let's dive in. We're going to give this talk about serverless ML solutions. And up here on stage, we have Vikram Tiwari, co-founder of Omni Labs.
And we have Martin here, who is developer advocate at Google Cloud. And to get started, what is Omni Labs? So Omni Labs is a company which is a startup based here in San Francisco. We are building tools to simplify and automate repeatable tasks. So repeatable tasks, you can think of, the example that we're going to do today is based upon analytics. One of the analytics tasks that marketers do, they get data from various sources where ad vendors, where they run their campaigns, and they download those reports, and they have to get those into one central place to take a look at the analytics of all those reports that they're getting from different ad vendors. So few engineering things that we keep on our side as ethos of engineering team is keep everything simple, make things scale on demand, and use machine learning to augment the users that we have of our technology. A machine learning solution is more than just building a model. Anyone can build a model, and we see so many of those come up on GitHub every day. But when we are talking about an end-to-end solution, it involves more than just the model itself.
What amount of work do you think you put into this sort of data engineering versus building the model, do you think, Vikram?
Yeah, actually, like building the model itself is really easy, because it's most of the time you are just taking a paper that is recently published, because you want to always be updated, and then you cut it down, you take the mathematics that is in the model to transform it to your Python function, or maybe if you're using Swift or something else, and converting that model code is not actually really hard. It's mostly like getting your data to work with that model, which takes more time.
Yeah,
as we are going to be talking about here today, when you are building this complete product, it takes a lot more to do that, because you have to extract and clean your data. You have to do that over time in a pipeline. You have to do and apply extra data transformations, because those are your new features that you have to apply. Then you have to manage this whole model pipeline that is there. So the configuration management of that, using hyperparameter tuning and similar things. And then your models are not good enough unless they can actually give value to the user. So you have to provide on-demand predictions to the users.
Right, and this never stops.
This
right?
never stops.
You don't build a model and you're done.
Yeah. So a product is like, it's not a one-time proof of concept. You have to build the model and keep the machine running. And there's new data coming in, there's new machine learning models getting out there, and you have to constantly give the value to the client. So for that, this is a whole pipeline. This is not a one way or one process. So there are a few engineering challenges that we had to face. We categorized it into 4 parts, and that's how we'll be walking today through the presentation. So first is extracting and transforming your data. So extracting the data, we are doing this via APIs from these vendors. These APIs have limitations that you cannot extract data all the time. It's not a socket-based API, or every vendor will have different restrictions. You have to have quotas on those APIs, and we have to honor those quotas, otherwise we'll get blocked.
Oh, it sounds like that might have happened in the past.
You know it. So then all the raw data that you get you have to also transform that data. So you have to transform the data for multiple use cases, because analytics is today's use case. What's next? Machine learning, of course. Then once you have all of this data, you want to store that in a central location where you can use it for reporting as well as analytics use cases. And then you can store it all for use cases of analytics, but your queries might become slow. So you have to make sure that your queries are always performant, and they should always be returning the results in a performant way. Users don't want slow queries. Nobody loves that. And keep the cost low as well. So you don't want to scale up the servers. We'll talk more about that.
Yeah, Omni Labs is a startup, right? So you're looking at costs quite a bit.
Almost all the day.
Right, and we'll see more about that and how to manage costs and make this all efficient.
Yeah. Then, once you have all the data, you have to actually build your models and keep them updated. Keeping the model updated is not just keeping the model code updated. Of course, you have to update your Python dependencies all the time. But you have to also make sure that it's getting the new data. There is always our advertisers, they are actually running the campaigns every day. So you want to get all the data every day or as much frequency as you can and generate the newer model, because your model is as good as the data that is getting in there. Then you also have to manage retraining, because there are new clients that are coming in. You want to use one central model for all the clients, or you want to generate new models out of those models, the central model that you have. And of course, hyperparameter tuning. Who doesn't want to do that? you never can build a good model by yourself. You have to use hyperparameter tuning to get the best hyperparameters. And finally, all of this is no value unless you can serve this in real time to your clients. So managing authentication, which client gets access to which model that you have in-house, depending on how much they're paying. And all of this managing in real-time predictions. And this traffic is very infrequent, as we will talk more in the more in the presentation today.
Excellent. So with this, a lot of this can be done in serverless. We've all heard about serverless. And serverless computing, there's one part of serverless that gets most of the press, most of the blog posts, most of the attention. And that is the central part of the figure here, the compute part. So serverless computing, just as a quick recap, in the Google Cloud platform, you could do cloud functions. If you have just very simple pieces of code, functions, you can string them together. Or if you want to deploy something bigger, like a full application, you would run those on App Engine. Yesterday, you may have heard the announcement about Cloud Run. That is the third hexagon we see there in the middle. This allows you to upload, deploy a container, and run that serverlessly. So serverless compute, OK, we kind of know what that is. But there's so much else, so much more to serverless. Because we, as developers, want to solve business problems, not engineering problems. So that becomes a lot easier if we do computation serverlessly, but also if we do data analytics, database storage, ML, DevOps, messaging, all these other things can be done serverlessly as well. And we'll see some cases here where Vikram will tell us how his startup, Omni Labs, achieved greater dev velocity by going serverless on some of these other pieces as well, not just compute. So first we have, Vikram was mentioning, extracting and transforming the data. So these data pipelines, as we heard, they extract the data from the APIs, they clean it, merge it with other data. And we have some engineering challenges here. It's not just a simple FTP import or something, and you're done.
FTP import, oh man.
Yeah.
So we are getting all this data from different APIs. We have to clean it. Of course, there's feature engineering that you have to do. And the biggest challenges that we faced on our side was the variability of the data size. Because there could be a client which is running a very small campaign, so they are getting 10 entries a day. Versus there could be a client which is running thousands of campaigns across geographies, and we are getting thousands of entries per hour. So data size varies from client to client. Plus, frequency of data ingestion could also vary. There could be somebody who is not running any campaigns right now. We don't want to keep machines up for those ingestions. Or there could be somebody who's running this and wants this data every few hours. And we want to make sure that our solution can deliver this to them.
So you couldn't have a sort of one-size-fits-all.
Yeah.
Is that what made this hard?
Yeah. So what we tried was, we tried to, as soon as you have a data problem, first thing you do, you write a Python code, put it on a virtual machine. So we tried that, but there were multiple issues there. What could happen is we could allocate access compute. So if there was data size was really small, and we had given it a 10 CPU machine, not really required. Sometimes it might be a really big data set, and we didn't allocate enough CPU or enough RAM in there. And RAM is not compressible, so it crashes the whole machine. That also happens. Sometimes this whole process, since it's happening in a chain manner, first we get the data on one machine, then we transform it on another machine, then we pass it forward to the third machine to push it into different storage sections. This whole process is chained together with different scripts. And if one of those breaks, the whole system collapses. It's very brittle, and the collapses, any breaking causes cascading collapses.
So this is, of course, managed VMs, as we heard. There is another way to potentially doing this. With Cloud Dataflow, you don't manage servers. It can take batch or streams of data, and then serverlessly dynamically allocate these jobs across physical machines, and you don't really see the physical machines or manage them much. Would that be something that would be useful for Omni Labs?
Yeah, so that's why actually we ended up doing. So we ended up utilizing Dataflow, And with Dataflow, what we were able to do is we were able to launch as many jobs as we can in parallel. So we split off our jobs into smaller chunks. As you can see from the image, we launched like 10 jobs within a minute. And all of these 10 jobs are running in parallel. And if one of those jobs fails, it doesn't cause any issues with another job that is running. So other systems can keep running, and one individual job fails by itself. Also, all the machines, since they are scalable by themselves, so if your job runs in 7 minutes or 7 days, your machines can keep alive. System scheduler will take care of that. And they can scale up and down as your data flow transformations are happening.
You had jobs that ran for 7 days?
A few, and some for more than that. But
more
yeah,
than that?
I didn't have the screenshots for those.
Wow, that's a big job.
Yeah, so we were doing most of these as batch jobs. We have started doing most of these now as a streaming job, so it's always running machines. There are some people who have done these jobs whose machines have been running for years now.
Wow.
Yeah. So while doing this, we came into touch with Apache Beam. Apache Beam is the programming model that you use to transform your data and run this on a data flow pipeline. Apache Beam provides you an out-of-box methods. So like there's reading from a file, or splitting your data into, or creating a flat map. Plus, you can create your own functions and apply those into the, utilize those custom functions as well. The best thing about Apache Beam is your pipeline options, as you can see on the top. If you want to take it away from GCP, you just change your pipeline options, and you are on your local machines, another cloud provider, or anywhere else you want to run it. And it's just change of configuration. Your code never changes.
You would, of course, never want to take it off of GCP, yeah. But just in case, it's nice to have an escape hatch.
Yeah.
All right. Yeah, you should never be a prisoner. If your cloud platform, whatever vendor you're using, is keeping your data and code prisoner on there, then it's probably not a place to be. You want to always be able to have the escape hatch. It's sort of like if you're on a plane, right? You probably don't want to use the the emergency exits too often, but it's good to know that they're there. So the next step Vikram was telling us about is filling the data lake. So data lake is this pattern where you're getting the data from various resources, like these APIs, external APIs, and instead of crunching it as you're importing it, you just store it all in sort of raw form. Then when you have certain data needs or reports or machine learning, that's when you apply the transforms. That means that you can do things like, I want to have everything by week and grouped by week. Or then next month you want everything grouped by hour. And you can get that because you have all the raw data. Now, so the data lake is the central source for all your raw data. You saw some real challenges here with filling the lake.
Yeah, so as I mentioned already, that there could be thousands of entries which could come in every hour. So what you want is a really good ingestion system which is write heavy. And then you also want to make sure that your analytics can aggregate really quickly, because you are going to be doing a lot of operations on different times and different window options. Plus, you also want to be able to do modeling on top of this data. So you will have different window sessions, could be really huge. It could be years of data that you could be using to do the modeling part. So the initial approach that we went with was dump and pray. So we took all the data that we were getting in through our pipelines and pushed all of that into BigQuery, straight up. And we demanded BigQuery to scale up, because BigQuery is BigQuery. The issues that we faced in there were anytime we had to update old data, it's a trouble. There are update operations in BigQuery, but you don't really want to do those. Those are really costly, and limitations are there. Plus, every time we were querying the data, we were querying all of the data. So the way BigQuery works is whenever you are querying a column, it has to go through all of the values in that column unless you limit it via some certain limitations. Plus, as we are storing all of this data from years worth of their campaigns, the storage costs keep getting added up. So we want to reduce that storage cost as well. So as you can see here, a query that ran on a small table, it cost us 32 MB to process that data.
So the 32 megabytes here is data that is pulled in.
Yeah, just because we are querying one of the columns in there.
And you're perhaps not even using
Yeah,
all of that
perhaps we
data.
only want to use like the first 10 rows because I want to only understand what happened in the last hour. I don't need to get all the data in there, but there's no way to put the limits around that right now.
So I see. And you have time series data.
Yeah.
And you typically are more interested in the newer data.
Generally, yeah. Clients
Generally.
don't want to see the historical data unless they were doing a meeting in end of the month. Yeah.
Yeah, yeah. And sometimes they want to see it all, but
Yeah.
most of the time, just the new stuff.
Yeah.
So for that one, there is a technique called date partitioning. So basically, you have this big table, but within BigQuery, you can tell BigQuery to partition on date, for example, and internally, BigQuery sort of splits it up into many small tables, so you don't have to query them all. Would that be a good fit for Omni Labs?
Yeah. Yeah, so that's what we ended up doing. We ended up with the approach of divide and conquer. So we took our data as it was coming in. We split it into the date chunks as it is coming in based upon the date that we got the data. We split it and put it into that partition. And using that, we could actually ingest a lot of data, even if it's a historical data. Earlier, we were like, we don't want to ingest all this data because it's going to be costly. Now, we could ingest all the data because BigQuery allows you to store older data. And if you're not querying on that, they reduce the pricing for you. Win. Who doesn't want that? It's an easy win. Plus, now that I'm querying on these partition tables, I can very easily limit those to a particular window. So as you can see in the query, we are partitioning it to just 2018 data. Even if I'm querying 2 years of worth of data, I've already reduced the size from 32 MBs of query to 9.7 MB of query. Query runs faster, gives me the result faster, and the costs are cheap. So I'm saving not only on the storage, I'm also saving on the queries that I'm making.
And you mentioned there was this older data is cheaper to store?
Yeah, yeah. So after 30 days, if I'm not getting the number wrong, if you don't access the data, if you don't update the data, you can still access the data. Accessing the data never gets, like there's no latency. You won't see the latency there. But it just becomes cheaper since you're not updating that data anymore.
Oh, that's nice.
Yeah.
So we talked here we heard about partitioning by date, putting limitations on date. There is, of course, this general purpose database that allows you to do all that. That is not BigQuery. So there is just plain old SQL databases you could run. And you can partition, or you can put limits on when you run queries on those. Could you tell us a little bit about why you're not going with a plain SQL solution?
Yeah, so SQL solution would have been perfect, because what you can do is next day when you get the data and you see the numbers are different, you can just go and update that number value. But SQL solutions are really easy to get set up, but really hard to scale. Think of, right now, I could have started with a small SQL instance, but as soon as I get more data, I need more disk space. As soon as I have more clients which are querying, I need to scale up my cluster because I need more RAM in there. I need more CPU. When there are a lot of clients doing this and they want to do this frequently, I want to add a caching layer in the front of that. And as clients scale on that, you add a cluster in front of that again. So it's just chasing the problem all the way down, and you keep scaling, and it never stops. With BigQuery, push it all in there. Don't have to worry about it ever again.
And SQL, Cloud SQL is somewhat serverful as well?
Yeah. So it's like you have to still do the capacity planning on your side. They can automatically do replication. They will do backups for you. They will manage it as a SQL database. It's not an analytics database. You want to use BigQuery as the analytics database for your workloads, yeah.
And you said, Vikram, that it's easy to get started.
Yeah.
So is this something that perhaps when you start building a proof of concept, you might go with SQL and then migrate to BigQuery? Or what are your thoughts?
Depending upon your needs. If your needs are not really, if you see that your clients are not going to be, it's either not too many clients, or it's not going to be too many frequent queries, or not too many aggregations, SQL might be a perfect fit for you. And you might have to maybe go to 2 or 3 tiers of scaling of your SQL instances. And you should do that. It's very easy to get started. But BigQuery is also easy. It scales.
Oh, good.
Yeah.
Excellent. All right. Those were 2 down, 2 to go. The third item, the third engineering challenge is keeping the machine learning models fresh. Because as we heard in a in a machine learning lab or when you're testing it out, you might build a model and you're done. But in a real company, like Vikram's company, these models have to be refreshed all the time for the new data that comes in. So these models must be updated all the time on the latest data. Could you tell us some about the challenges you run into when updating?
Yeah, sure. So think of like when you build a machine learning model, we used last year worth of data to build that model. Now next day, I'm getting new data, which is only 24 hours of data, but I want to make sure that my model is fresh. So I will have to use this 1 year worth of data plus this 24 hours of data merged together and then retrain my whole model. This works, but every few days, you're going to keep increasing the size of your data. So the retraining time will, every few days, you will see it increasing. And there's no way around it. Or is it? There is a way. So we'll talk about the way in a minute. Another issue that we had was we don't want to keep rebuilding these models for every new client that we get. If all the clients that we are getting are trying to do the same problem over and over again, you don't want to rebuild the same model code and redeploy those same pipelines all the time. You want to use the same version, same model, retrain that model, and utilize that model for all the clients if you can. So what we want to use is a central model, but retrain that for the specific data for the client. So our initial approach was using XGBoost. XGBoost allows us to build linear models or random forest type models, and you can very easily scale the parameters in here. So as we got more clients, as we got more different types of clients or different types of options that they wanted to include, we built a lot of models, and the model size was increasing. So as we see here, like initially we started with, on week 1, we have a smaller model. On week 2, we get model size keeps getting bigger, and data also keeps getting bigger. The compute time takes getting bigger. Everything keeps getting bigger and bigger. Model retraining also takes a lot of time. Our clients are not satisfied if you take more than 24 hours just to give them a real-time more predictions, like on the new data. Plus, we have to manually maintain the whole model deployment lifecycle. Every time we get a new model, you have to make sure that the older model gets phased out. You want to deallocate the resources, compute resources that are available there. Maybe you want to keep them, because maybe the new model doesn't work really well, and you want to really quickly switch back to the older version as well. So there's a lot of toil that goes in there in maintaining these models.
Yeah, I guess you could theoretically end up in a place where it takes more than 24 hours to process the last 24 hours,
yeah.
Which means you never catch up.
Yeah, and it happens as soon as you have more clients and a lot of data coming in, you will face that problem.
You will.
Yeah.
Oh, that sounds like a good problem.
It's a good problem.
Lots of clients.
I don't mind the problem.
Yeah.
Yeah.
Yeah, so one thing to consider in this sort of situation is TensorFlow. Running TensorFlow on ML Engine, which is serverless. You don't have to set up servers. Scales better. You get these sort of checkpoints and API versioning that Vikram was just talking about. You get those built in, so you don't have to manually deal with them. And of course, because it's serverless, you can then focus on your models and not ops. Is that something that would fit for Omni Labs?
Yeah. So we ended up actually using TensorFlow on machine learning. So rather than using XGBoost models, we ended up moving all of that to TensorFlow. With TensorFlow, it provides you the ability to retrain your models only on the new data. We use checkpointing. With checkpointing, you train your model for the 1 year worth of data. You create a checkpoint on that time. And next time when you have to retrain your model again today, you get the new data, start from the checkpoint, and you retrain your model on the new data only. Training time is much faster. The only time we have to take longer time is when a new client comes on board and we have to retrain the model on the whole of their data. Then another problem that we had, retraining for all the different clients. Now, with TensorFlow, there's a concept there called transfer learning. So we built one big model, and anytime a new client comes in, we use transfer learning to transfer the parameters and weights that we have learned across our clients on to specific, based upon the needs and constraints of a specific client. We retrain that model, and now we have a new model. And we can keep retraining our global model and lower split of model for each client based upon their own data. Plus, we ended up using wide and deep model for this. I'll talk about that in a minute. The best point with this was we reduced the cost so much that we don't really see any increase happening. It's always a flat line.
And does this mean then that if I come on as a new customer, maybe I don't have a whole lot of data I'm bringing with me,
Yeah.
you can still serve decent predictions because you have a good model for all your other clients?
Yeah, so this helps in new clients as well, because new clients haven't tried all the geographies. New clients haven't tried all the different parameters that you can run their campaigns upon. Since we have seen this across our clients, we can give them optimizations and recommendations on how to run their campaigns because we see a full picture. And we don't have to wait for them to get their data. We know their constraints. We can retrain the model based upon their constraints.
So the more clients you get, the smarter your company becomes.
Yeah, it feeds on data.
Yeah, virtuous cycle. I like that.
Yeah, so I talked about wide and deep models. When we started using, moving away from TensorFlow, moving away from XGBoost to TensorFlow, we stumbled into this. This was very recent at that point in time. Wide models are really good for memorizing stuff. So if you want to make sure that whenever you are doing a targeting on a single place, you want to make sure when you are targeting San Francisco, you also get Oakland in there. So those models will be really good at that because they understand this whole thing is the Bay Area. Deep models are really good at generalizing. So if you want to target San Francisco, they might also suggest you that you should try Austin and New York because those are tech hubs. And it has learned that because of those are deep neural networks, because of generalization, their ability to generalize. But what happens with deep neural networks is those are not really constraint specific. You can't put some constraints in there to say, I actually don't want to use this. So an option is, if you want to get recommendations for teenagers, you don't really want adult recommendations in there. You just want it for teenagers. So you want to put those limitations in there. For these kind of problems that we have similar problems. For this, we ended up merging these two together. This is not our research. Research is by Google team. We used wide and deep models. There are papers published for this. And to do this whole thing, we could have written the whole code from our side. But TensorFlow provides an easy way to utilize wide and deep models. They have the fully featured API. All you have to do is connect your data into it. You can optimize and tell it exactly which features are the cross features that you want to utilize, which ones are the deep features that you want to utilize. You can put your constraints in there. Plus, you don't have to manage how the data will get distributed, how the training will happen. TensorFlow will take care of all of that. If you put it on machine learning engine, it will take care of scaling the machines for you. And you can do hyperparameter tuning as well there. So you get the best model architecture by using wide and deep, and you get the best model accuracy because of using hyperparameter tuning on Cloud ML engine.
Oh, so it's kind of the best of both worlds.
Yeah.
If you combine them.
Yeah.
Oh, really nice. All right, so all of this shuffling data around, all of this tuning models, all of this stuff accounts for nothing if you don't actually are able to make predictions in the end. So making predictions, I understand that this is something where you told me customers come in on Monday morning, they all sit there, they all hit the report, and then what used to happen? What was the challenge?
Yeah, so the challenge that we face is like nobody cares about their campaigns on Friday. Everybody wants the reports on Monday morning, and they want all the suggestions because they want to apply all those suggestions now. So every Monday in the morning, we would see a lot of traffic come in.
You couldn't tell them that, hey, you guys, you start on Tuesday, you start on Wednesday.
We wish, like New York, you can only start in the morning at 10.
They all wanted it Monday morning.
Yeah, everybody wants it in the morning at the same time. And that puts a lot of load on your servers, no matter how much you scale. And scaling, can't talk about that. OK, so the approach that we went up with, OK, if we are seeing more traffic come in, let's increase the machine size. Let's add more machines into this cluster. As we see more and more users come in, we kept increasing those machines. But it's not really possible all the time, because you can keep increasing the machines, but from Thursday to Sunday morning, Sunday evening, nobody's using those. Nobody's querying on those. So all the machines that you have scaled up there, you're just paying. I don't mind paying them, but I don't want to pay them all the time.
Please pay us, yes.
Yeah. What would happen, though, on Monday morning, no matter how much we had scaled it up, it would still go to 100% CPU, because everybody's trying to do it at the same time. Everybody's querying the servers. And machines would become unresponsive. You don't really want your machines to go down. All the hard work that we did on getting the data, transforming it, putting it everywhere, building these machine learning models, all of that fails if you are not able to serve your clients properly.
So what would would actually happen? Would they crash? Would they slow down?
Yeah,
what
so
would you see?
it starts with like the first person who gets to query gets the result really quickly.
Yeah.
But after that, slowly and gradually starts slowing down, unless like we see it and we increase the machines in the cluster. But it gradually slows down, and once the CPU reaches 100%, it just becomes unresponsive. Nobody's getting any predictions today.
Nobody's getting anything.
Yeah.
Oh, yeah. No good. OK, so it sounds like a very variable load here, and a lot of systems have that. I mean, most systems that all of us build are probably very variable. Not very many people hitting our stuff at 3 a.m., right? But more people hitting it, say, Monday morning. So one possibility here is to let Google handle the scaling up and down with Cloud Functions. Cloud Functions is sort of the gateway, can be one of your gateways into the Google Cloud. Once the user hits a Cloud Function endpoint, an HTTP, you can have code in there that can then hit cloud storage, machine learning, Bigtable, all these other products that are in the cloud platform. And that ingestion point that a Cloud Function is, that gateway into GCP, it scales up and also scales down, so you don't pay when people aren't using it. Would that be a good fit for this Monday morning problem?
So with Cloud Functions, there's no server management. It automatically scales up and down. You only pay when you are running your code, and it runs in response of the events. That's the best part. Plus, it connects and extends to all of the existing Google Cloud functions that we have, all the internal systems, either it's machine learning engine or any other APIs that we have. So that's what we ended up doing. Our new approach was to go serverless. We went with Cloud Functions. Our error rate and latency dropped to almost 0. It's still an error because users are not trying to they're trying to get predictions on a very different data, or something that our model doesn't exist even, or a totally new client who wants to get their predictions just right now without even running any campaigns. If people do that. So we were able to scale up on Monday mornings. As the load came in, it will automatically scale up. And whenever there's no more requests coming in on Thursday on to Sunday, it will just scale down itself. To write that code, it's really simple, actually. It's one single file that we use across all of our clients. What we do is, whenever a different client comes in, all of those model names and authentication parameters, along with the data that they want to request to get predictions upon, all of those get passed into one single endpoint. And based upon that, we make the correct request to machine learning engine to get the predictions. And one single point enables all of this scale up and down. We don't have to manage all the code. It's just one single place code to manage. Error handling is hidden there because error happens. Yeah.
Do happen.
So to wrap up, initially, this was our approach where we were hoping for no alerts. You can hope for that, but you will still get that. As you can see, our failover replica was also getting 100% usage in there. So
you had a failover replica,
yeah,
and the failover
was also giving
fell over.
Yeah, you can never have too much compute. Yeah, so we started, we had compute engine for our serving instances. We have compute for our machine learning tasks. We had compute for our data ingestion tasks. Everywhere, it was compute engine. But we moved from there into a completely serverless solution, where we focus only upon what matters for our business. So clients now query to Cloud Functions. Cloud Functions get the data from, get the predictions from ML Engine. And on the other side, we query and get all the raw data from external APIs using Cloud Dataflow, push it to BigQuery, and Google Storage, Cloud Storage for our machine learning modeling tasks.
Oh, sorry. Yeah, I was going to say, you make it sound very easy here. Yeah, we used to do it this way, and 100% CPU, and we switched over. I mean, you're a smart guy, Vikram, but could you tell us a little bit about your journey from the serverful world to the serverless world? It must have been a lot of work.
Sure. So yes, serverless works really well. But the best thing to do that you can do is trust the Google or any other serverless solution, but verify on your end. And no, you don't need blockchain. So to do this, the best way to get set up is set up your monitoring and alerts. You want to make sure that your services are up, and you are constantly monitoring, like we did for BigQuery. We wanted to monitor how our queries were doing. So we are looking at the latency for our BigQuery queries. So monitoring and alerts will make sure that your systems are up and they are actually doing as you would expect them to do. But sometimes you actually need a view into these systems. These systems are black boxes. You can't really SSH into these machines and tail the logs. So what you want to do is you want to set up the systems in there so you can actually get the logs in the real time. So we use Stackdriver logging, which enables us to get all the logs from all these clusters that automatically scale up and down. You don't have to do anything in there, and it will just get all these logs to this one central platform for logging. And you must write the good code, but I don't. So we still need error tracking in there, because there are some exceptions that only happen on server in production. So for that, we ended up using Stackdriver error tracking. So any exceptions that we are not catching, there are a lot of times that you deploy something in the real time, and you make mistakes. So make sure that there's something that can catch those exceptions, and rather than failing abruptly, you fail gracefully.
And you drew some blue hexagons here. Let's just make sure I understood. The first one for monitoring and alerts, that was Stackdriver
monitoring.
Stackdriver monitoring.
Yeah.
And for logging, it was Stackdriver
logging. It's so easy.
Oh, I have a guess what the last one is called.
Sure.
Stackdriver error tracking. Oh.
Yeah.
So the cool things with these is that they're all serverless. You don't have to set up servers that manage the monitoring and logging and error tracking. If you have a Google Cloud Platform project today, you can just click on the hamburger menu up on the left and turn on these services in your account. But you did, so you set all of this up. This took some time to migrate everything over?
So our whole journey it's not a turnkey solution. It takes time to rewrite your code from Python to Apache Beam, and using a big Node.js project to one single function to do all these predictions. It took some time, and adding all these features in there. So this is a multi-year journey that it took from almost a year end to end to build all these solutions and run it totally serverless. Yeah.
All right. Very good. Should we do the last slide, Vikram?
Yes, let's do it.
Let's do it. Should you or I click?
Done.
You clicked.
Yes.
Excellent.
So
together,
solve your
business problems. Not engineering
problems, and go serverless.
Go serverless.
Yeah.